we are going to move on to 3.8 alpha lesson. Okay, so we're going to start now. Ready? This is not on the assessment at the end of the week, but there is implicit differentiation involved in this lesson, and that would reinforce how well you understand it. So first thing is, we'll start with a problem from the end. The domain of the inverse sine is -1 to 1. Justify your answer. So true or false is one thing, but they were, explain why is that your answer? My answer is true because of this. My answer is false because of that. The domain of the inverse sine is x is between -1 and 1 inclusive. True or false, and why? Well, I would go here. I go to the calculator, go to y equals draw the sine. There it is. Okay? There's the sine wave. What do you see? Well, I see the sine wave is a function because it passes the vertical line test. It fails the horizontal line test. What does that tell you? Its inverse is not a function. The fact that the sine wave fails the horizontal line test is helping you anticipate that its inverse will fail the vertical line test. But if we limit the domain to just -pi/2 to pi/2, then the sine function is a 1-to-1 and it passes the vertical line test and the horizontal line test. Or are you having flashback to sitting in front of Mrs. Bratz? That's a positive thing. Yes, we did this. I remember. I don't remember every little detail, but now I can remember when she went over this with me and I saw like this was important and that maybe not so much. So you restricted domain of the sine wave. So the restricted domain is -pi/2 to pi/2. Fourth quadrant and first quadrant. And then the resulting range is -1 to 1. So if we go back to this, true or false, the domain of the inverse sine is -1 to 1 and why? Mrs. Bratz would be very disappointed. Or your pre-calc teacher who was someone else might be disappointed. Anna. It is true. Why? Because when you take the inverse function, which is what this is, x goes to y goes to x. Domain goes to range goes to domain. So for this problem, I would say the domain y equals sine x. The restricted domain is -pi/2 to pi/2. The range is -1 to 1. For the inverse sine, they switch. So -1 to 1 becomes the domain, and -pi/2 to pi/2 becomes the range of the inverse function. Okay, yes, that's stuff you did in pre-calc. So the one thing you have to be concerned about, or not concerned, but careful about, in the textbook, the heading of the section is inverses of derivatives, inverse trig functions. But College Board holds you accountable to more than that. College Board holds you accountable to derivatives of inverse functions, not just the inverse trig functions. So what's happening here? The pre-image, you have x and y and the H chart. The third column is the slope, the derivative, which is delta y over delta x. For the inverse, these switch. So you have y and x, and the slope is delta x over delta y. Now, we're going to remind you of the array how we're writing the trig functions, sine, cosine, tangent, cotangent, secant, cosecant, and we're going to write them the same way for the inverse functions, and it's going to be important. It's going to be helpful to help you recall this. Now, ready? If everything's important, nothing's important. This is not as important as implicit differentiation, okay? This is not. If you had to choose what to focus on, yes, 3.6 and 3.7 is what you focus on. This will come up in itself, maybe one, maybe two questions. It'll come up when we get to chapter 6, and I'll remind you of that. But implicit differentiation is going to come up every day. So here's the picture we showed you, trying to communicate to you the sine wave where the restricted domain is, where it's going to pass the vertical line and horizontal line test. And we're going to go to right to example 1. And that's the derivative of the arc sine. Now ready? Arc, that prefix, is old school. It means the same thing as the inverse symbol. Arc sine and inverse sine are the same thing. If your parents have their calculus book from college or high school, like in their professional library or in the basement or in the attic, and you were to look this up, it would probably use the terminology arc sine. And College Board uses this also. They use both. So I want the derivative of that. So in the book, you have y equals inverse sine of x. Okay? So this is what we want the derivative of. Where's that coming from? It's coming from here. And the inverse of this is exchange x and y. X equals sine y. So this and that are the same thing. So in the book, they wrote x equals sine y. Here comes the differentiation. We differentiate the right side. The derivative with respect to x of x is 1. But now we're on the other side. So on the left side of the equal sign, you need to see this. And this is what you're going to have to do on the test. You want the derivative with respect to x of the sine of y. This variable and that variable don't match, which is why you have to use the chain rule. You have to use dimensional analysis. Like somebody asked this morning, like where'd that dy dx come from? Well, that's thought. I mean, that's what you need to do. You need to verbalize your questions. Not sit there and just, well, I'm going to put it there because he wants it there. It comes from here. If I want the derivative with respect to x of something that has a y in it, that's going to equal the derivative with respect to y times dy dx. Because this is what I wanted, and those would reduce, and that's what I wanted. So in order to do that, you would take the derivative of this thing with respect to y. And the derivative of sine y is cosine y. But you need the dy dx for the dimensional analysis, because this, you took the derivative with respect to a different variable. And the more of these problems, like I'm not a fan of saying, do 1 to 31 odd. But you need to do a few of these problems to get the hang of this. So in the book, they get cosine y times dy dx. Well, dy dx is what we want. That's the change in y with respect to x. So you just divide both sides by cosine y. Okay, so far so good. You undo what's been done to dy dx. And then they introduce the Pythagorean identity, which is cosine squared plus sine squared equals 1. They're going to use this here. Okay? So you learned these last year. You don't need to learn any more than one of them. If you know this has 1 by itself. Algebra 1. You could add a negative cosine squared to both sides and get sine squared by itself. You could add a negative sine squared to both sides and get cosine squared by itself. And I didn't write out what it equals because you didn't want to clutter up the table. Then you could take 1 divided by cosine squared theta and multiply it by both sides of this equal sign. 1 divided by sine squared theta divided by both sides of this multiplied by both sides of this equal sign. And you would end up with 9 trig identities based on you manipulating just this one. So back here to the derivative of the inverse sine. Cosine squared y plus sine squared y equals 1. So cosine squared y equals 1 subtract sine squared y. Take the square root of both sides, and you get this. 1 subtract sine squared y. And they went up here and said, well, sine y equals x. So where there's a sine, we're going to put x. And you would get 1 take away x squared under the root sign in the denominator. If it were a mu instead of an x, you would have this 1 over the square root of 1 take away mu squared d mu dx. Now, you are not accountable for the derivation if you memorize it. There's not that many things you have to memorize, okay? All you're going to do today, you get to do your favorite thing in math. Your favorite thing in math, which is how things worked when you were at ETR or St. Francis or Holy Cross, was plug it in. That's all you're doing. So if I look here at example 1, I'm using that algorithm and just substituting. Here's example 1. They want the derivative. So this is the position. This is the parent graph. The inverse sine of x squared. You want the derivative. What do you do? Where there was a mu, you write what mu equals, x squared. Here's the algorithm, x squared. The derivative of x squared is 2x. Take that x squared, raise to the second power. Multiply the 2x out front. That is the derivative. Done. Meaning you don't derive it from the beginning, what they showed you in the textbook. You're just taking the algorithm and substituting the value, as long as you memorize the algorithm. Now think about this. Last year, the AP test was open book. And maybe you took some AP tests. So people are saying, well, why am I bother memorizing this? That test was so compact. And the 25-minute question, you had to do so much work. There was no time to look things up. Talk to people that took it. You looked at the clock on the Chromebook and see the clock ticking down, and you had to go from question part A to H. The people that cut corners and said, I'm going to look it up, just got lumped up. So that's your model. We don't expect you to memorize it yet. That's your model, and you're doing problem number 3. So I wrote it backwards just so it wouldn't look like the t was under the root sign. So root 2 is your coefficient. But all t times root 2 is your mu. When you square that, you would get 2t squared. The derivative of this thing's root 2, so you have root 2 over that. Done. And what happened? You did the derivation of the inverse sine. And we're going to, over the alpha and beta lessons, do the derivation of the inverse sine, tangent, and secant. We're going to do every other one and show you how they're related to the 3 that we didn't do, instead of doing implicit differentiation for all 6 of them. So next one is inverse tan. We're back to this table. This is an identity, which is going to be used in the derivation. Textbook. I want the derivative of the inverse tan. Y equals the inverse tan of x is the same thing as saying tan y equals x. Yes, I get that. The derivative of the right side is going to be a 1. The derivative of tan y with respect to x is secant squared y dy dx. You need to know derivative of the tangent for the quiz, and this was the derivative of tangent y with respect to x. So the dimensional analysis, you have the dy dx. Divide both sides by secant squared y, then this gets substituted from secant squared y from the identity. That step right there is from here. Instead of secant squared y, they wrote tan squared y plus 1. Then what? Well, tan is x. So you just get 1 plus x squared. And if we're a mu, you would have 1 divided by 1 plus mu squared times d mu dx. So example 2 says this. This is your position, the inverse tan of root t. We want the velocity. So we just go to the algorithm, and where there's a mu, we paste root t. The derivative of mu, the derivative of t to the 1/2, is 1/2 t to the negative 1/2. Then they tell you at time 16, here's my table. At time 16, this is the position, the inverse tan of root 16. This is your velocity. Okay? So that's staying up there, and you're going to problem number 11. If you are at home, you're going to do 11, and then you're being dismissed to go to AP Classroom to do the exit ticket. But you're going to stick around until we do problem 11. So for 11, ready? The derivative with respect to t of t is a 1. And mu is just t. So you just get this. At time 2, the position would be inverse tan of 2, and the velocity would be 1/5. That's it. Now, that is the alpha lesson. So, for the children at home, we will see you on Thursday. You're taking the quiz on Friday.